Hey guys, welcome back to General Chemistry. We're going to do a little bit more development of the quantum theory. So in the last video, I left you with the double slit experiment, the fact that waves will diffract through the double slits, interfere with themselves, and give us this area of light, dark, light, dark. And then I told you that we did that same experiment with electrons, and we get the same results. We get a diffraction pattern. So what that kind of indicated to us is that electrons behave like waves. Easy, right? Not so fast. Today we're going to talk about the photoelectric effect. So the photoelectric effect, it's going to take a little bit to build up what this experiment should have looked like, and then what the results were, and at the end of the video we'll tie it all together as to what it tells us about electrons. So the photoelectric effect is as follows. If I were to shine light at a piece of metal, that metal will emit or eject an electron when the light is shined upon it. Okay. Scientists were interested in how this happens, why this happens, and then, like any good scientist, what are some things we can do to make it behave differently? So the scientists, before conducting experiments, they wanted to predict the why and how of this. Like, why is this happening? How is this happening? And can we predict what might happen if we do something differently? First, I need to talk about binding energy just quickly. Binding energy is just the energy needed to overcome or in order to dislodge the electron. So when I talk about the energy that's holding the electron on, we're just talking about binding energy. Just a little terminology, just in case I use it again. So prediction. At this time in science, scientists felt like they had a very good understanding of Newtonian physics, how things behave, velocities and force and all sorts of stuff like that. So applying their Newtonian physics to this photoelectric effect, they're like, easy, I can predict what's going to happen. The first thing I predict is that the higher the amplitude or the shorter the wavelength, the easier it's going to be to knock off the electrons. Okay, makes sense to us, right? So shorter the wavelength. Okay, shorter wavelength means it has a higher energy. Okay, so something that would have more energy. So if we think about throwing a ping pong ball against a glass window and throwing a baseball against a glass window, if I throw them with the same force or the same speed of my arm, we would expect that baseball to have a bigger impact on the window, correct? So that's essentially saying shorter wavelength, higher energy, baseball is going to cause more damage. Amplitude, intensity. So if we say I'm going to hit a piece of metal with a higher amplitude light, that's a more intense light. So we can think about hitting a piece of glass with a bat. So low amplitude would be a soft swing. I just kind of tap the piece of glass. High amplitude would be a really hard swing. I just really whack that glass as hard as I can. We would expect the higher amplitude, higher intensity swing would cause more damage, would cause the electrons to come off easier. Okay, so those are the two analogies that I can think of. But again, Newtonian physics, pretty easy to understand. And then conversely, low amplitude or low energy light, there would be a lag in ejection time. So what we're looking at here is that, even though we hit the glass with a ping pong ball, or we just simply tap the glass, eventually that glass is probably going to not be able to take any more abuse. So the analogy here, probably a better one would be like nail into wood. So even if I tap a nail very lightly, eventually it's going to make its way into that piece of wood. So that's what we're saying about here, a lag time. It may take a long time for that to happen, but it still will happen eventually. Okay. So basically summarizing all of this, the kinetic energy of the electron coming off, so the force or the speed with the electron that is ejected, would depend on the brightness of the light. So higher amplitude, probably going to have more kinetic energy as it comes off. Shorter wavelength, so a more energetic light, electrons are probably going to come off pretty quickly. Makes sense, right? What did we observe? What was reality? So let me break this graphic down for you. So here is the results. So moving from left to right, we're talking about the frequency of the light. So remember, frequency, energy. So over here on the left, we have low frequency, low energy, so ping pong balls. Over here, we have high frequency, high energy, baseballs, right? And then going from bottom to top, we've got that rate of electron ejection. So how fast that electron's coming off that piece of metal. So rate of ejection of the electrons. So what happened? Well, we hit the metal with a ping pong ball. Then we hit it with a tennis ball. Then we hit it with a baseball, and all the electrons came off. Well, then we hit it with a basketball. Nothing happened. We hit it with a bowling ball. Nothing happened. We hit it with a rock. Nothing happened, right? So what this graphic tells us is there is a sweet spot, a threshold frequency, a perfect frequency that causes all of the electrons to come off. Even if I hit it with a ping pong ball, they're not going to come off. Even if I hit it with a rock, they're not going to come off. I have to choose the exact perfect ball, and all the electrons will come off at the same time. Okay? Not what we guessed. And then also, there is intensity. So higher intensity light, lower intensity light. Okay? So bright light, dim light, or the analogy we talked about before, swinging really hard with a bat, swinging very gently with a bat. So it turns out it doesn't really matter how hard we swing. All the electrons come off if we picked the right frequency. Okay? So I swing the correct size bat gently, boom, all the electrons come off. I swing the correct size bat really hard, boom, all the electrons come off. But it didn't matter how hard I swung the bat. They all came off because I picked the right bat. This is weird, right? So in reality, we found that it was independent of amplitude, independent of intensity, independent of how hard I swung the bat. No matter how hard I swung it, as long as I choose the right bat, they all come off. And it depends upon frequency. There's a threshold frequency. Duration is not a factor. So even if I use a bowling ball, for example, and I hit it with a bowling ball, and then a bowling ball, and then a bowling ball, and then a bowling ball, even all of that abuse still is not going to cause the electrons to come off. It has to be the right ball in order for them to come off. Okay? So what we see here is, instead of talking about baseballs and bats, we see actual results. So I use a red light. Red light has a longer wavelength, lower in energy. And we see no electrons come off. I use a green light. The green light is a little bit higher in frequency, higher in energy, a little smaller wavelength. I see the electrons come off. And then I use a high frequency light, a purple light, so lower wavelength, increase the frequency, and we see electrons come off again. So the sweet spot for our electrons was right here in this green-purple region. Anything to this side, they wouldn't come off. Anything over here, they wouldn't come off. What's going on? Well, you know when Einstein shows up on a slide, things are about to get real. So here's what Einstein had to say. Einstein proposed that light maybe wasn't a particle. Or maybe light wasn't a wave. Maybe it's like little packets of energy. So instead of light being this nice smooth wave that we like to consider it, maybe light is packets called quanta or called photons. Okay. And then light is composed of this stream of tiny particles that travels at high speeds. So light's a little lumpy. So what the photoelectric effect proved to us or to scientists is that maybe light isn't a wave. Maybe light is a particle, which would help us understand if light sometimes behaves like a particle and electrons sometimes behave as waves. Maybe there's this whole realm of physics that we need to explore. Maybe Newtonian physics isn't enough. And this is where scientists started to open the book on quantum mechanics. So quantum mechanics is just a different realm of physics. Instead of looking at things that we can see, touch, and feel, quantum mechanics gets on this teeny tiny quantum level. It gets on an electron's level. It gets on a photon's level. And as it turns out, things behave a little differently down there. Okay. So that's it for building up to the quantum theory. In the next series of videos, we're going to dive headfirst into the quantum theory. So bring all these ideas together and talk about what's really going on. I hope you guys found this helpful.